Okay,
Hello.
welcome
Yep.
back. Yeah, welcome back, everybody, to the third episode of the Math and Physics podcast. I'm Parker.
And I am Ray.
All right, let's get this started. Um, I was gonna say something, but I forgot. Should we just jump into it?
I think we can just jump into it. So I think by
All
the
right. right.
title, you guys already know that we're talking about constants,
Once
right?
again, the cheeky title comes into play.
Yes,
Yeah.
sir.
So we're talking about constants in nature that are just universal. We're going to talk about like mathematical and physical constants in this podcast. I am actually really interested in universal constants, and I know, like, I searched up on Wikipedia before um, recording this. I searched up like constants in nature, and there's like a whole list that like we just haven't learned yet. And obviously, I saw the ones that we already know, and then got a little bit of facts that I will mention later.
Yeah, so like I kind of also agree with you there that universal constants, number one, at least in my mind, are pretty cool. The fact that they don't change wherever you are in the universe, and they're pretty much always constant, hence the name. And I think it's just a
Yeah,
pretty interesting, concept or interesting fact about the universe that like there can
yeah,
be just
yeah.
one
Some
constant
things
for
just
this
some
for
things
something.
just don't change at all.
Yeah,
Which,
that's pretty
like, the
cool.
most obvious one, obviously,
Hmm.
the speed of light, which, in a vacuum, of course, is what is it, like
It's actually
three
like two
times
nine
ten to the
nine,
eight?
but like yeah,
Yeah,
three ten
299
into
times
ten to
10 to
the
the 8
8 meters per second. Yeah, it's pretty
meters per
fast.
second. Yeah,
But
it's super. It's unimaginably fast,
yeah, and
really.
originally I believe like it was kind of postulated as the speed of causality. And I used to
Hmm.
remember what C stood for, like in Latin, but I
Yeah.
completely forgot. And it's something pretty interesting too, but it has something to do with pretty much not light at all, because that's not really where the speed is derived from. It's
Hmm.
just that
Wait, where is it
because
derived from then?
yeah, because the thing isn't that the speed of light isn't because of the photons necessarily. The speed of light is actually like the maximum speed that anything can reach. It's just like a coincidence, not really coincidence, but the fact that the photons are massless. Now, because they're massless, they don't interact with the Higgs
Oh,
field, right? And that's the only reason that they can go to the fastest speed. So the speed isn't
dang.
dependent on the photons. The photons are dependent on the speed. And
I
this is
actually
like
didn't
a
even know that.
yeah, and this is like a big kind of like a misconception about which one depends on which.
So, like, the maximum speed limit of the universe was discovered before it was associated to the speed of light.
Yeah, exactly. Which is
Dang,
pretty crazy.
I learned something new.
Yeah, also because it's just mainly that because light doesn't interact with anything because photons are said to be massless, right? It's mainly
Mm-hmm.
because that property is what allows light to go so fast, right? Because of
Yeah,
its zero mass properties. And
yeah, and
gluons, I believe, are also massless particles that travel at the speed of light. And the hypothetical graviton, the force carrying
yeah,
particle of gravity,
yeah.
also said to travel at the speed of light.
Hmm.
So
Well,
yeah, I mean, there are a lot of things that depend on the speed of light. So that's what I'm saying. It's not really that they depend on photons; they just depend on this highest speed in the universe, which happens to
yeah.
be the speed of light.
So, like, the book I'm reading. It's like The Search for Many Universes.
Mm-hmm.
Um, in like one of the first few chapters, I think I told you about this. They talk about like the different types of vacuums that can be found in space, and there's like there's specific names for them which I don't remember, but like there's the regular one, which is the one we're living in now, and then there's like two higher energy vacuums that exist, and in the second, like, on the scale of energy levels, on the second highest, um, it's where electrons don't have a mass,
Mm.
and I'm guessing they also travel at the speed of light,
Yeah, yeah.
and that, like, in that state of vacuum, like, decays super rapidly, and so that's why we can't, like, there's not like huge subsets of the universe that are
Yeah,
just, well,
because if
actually we
electrons
don't
were
know.
massless, but if electrons
To
were massless, like stuff wouldn't exist
Yeah, I
because
know, but
electrons would just be flying everywhere.
I was gonna say there's not like super large spaces in the universe that are like in that state of vacuum, but really we don't actually know. Like
I mean, to be honest, we
there,
really don't know much. This is
there
all
could be.
speculation at this point.
Yeah, and at the same time, well, no, the vacuum states aren't speculation. Like that was like an actual thing.
No, no, but
But
it hasn't. There's no experimental proof
I think there is.
that electrons are
Uh,
massless.
like, yeah, in some states of vacuum, vaci, I think.
Oh, that's
Something like that.
something I learned today as well.
Yeah,
Thank
yeah,
you.
yeah. The
That's
thing
pretty
is, like,
interesting. I did not know that.
yeah, as I was reading it, like, yeah, the three states are like real things and they have like real properties. But as I was
Mm.
reading it, like my level of comprehension in that like subject is, beyond me. Um Wait, that sentence didn't make any sense. But yeah, I wasn't fully grasping what was being said, and I'm just relaying the info
Yeah,
that
because
I
that's a
that I
pretty
read.
weird fact that because the entire point that electrons are electrons is because they have mass. Negligible, but
Yeah.
still they have mass.
Yeah, I
Like
think that's
I
one
don't
of the
understand
reasons.
how electrons can even have zero mass because if they did then they wouldn't really what would there be? I don't even know.
I don't know. It's like I think that's one of the reasons why it decays so rapidly is because like the
I guess
properties
so.
of the particles are just all wet. And like I could be just mis misunderstanding the entire
Yeah, maybe we
chapter,
need to
but
read that article.
yeah, I mean, I'll give you the book,
Yeah, for
when
sure.
we, yeah. So yeah, do you remember in class when we were learning about like waves and oscillations? We started
Mhm.
with like the mini like history lesson,
Mhm.
um, and like was it Huygens who like who thought that light like came out of our eyes, and then when it hit something it would reflect back into our eyes, and then we would register it as like a thing,
What the hell? That's a crazy theory.
yeah, it's a crazy theory, but like this is like really back in the day,
Yo,
like
that's
they
nuts.
thought, I don't know who it was, I think it was Huygens at first.
Who's
um
Huygens?
the double slit guy.
Heigensberg? Wait, what? No, that's not his
No,
name.
i
Heisenberg.
think it's I think it's Christian Huygens.
Wait, like Heisenberg's uncertainty principle?
No.
Then what
No,
are you
bro, the
talking
double
about?
slit, the guy who did the double slit.
Isn't that Young?
The double
Young and
Young and
Fresno.
Huygens. Young and Huygens.
It's Young and Fresno.
No, it's not.
Yes, it is.
Bro, I swear to God.
It's Young and Fresno double slit experiment. I think.
Okay, I'm Googling it right now. Okay,
Me
Christian
too.
Huygens. Um, he's a Dutch physicist. I'm just gonna control F and look for double slit. Yeah, yeah, he did it, bro.
No. By
Huygens
the
had
French physicist,
experimented.
this guy Fresno. It's Fresno, bro.
Okay, anyways,
Fresnel
it was.
contributed significantly to the establishment. Okay, you know
I
what?
mean,
Let's agree to disagree.
I'm looking at the page right now, and it says he experimented with double refraction.
Listen,
And
Parker, let's just agree to disagree and move on.
all right, all right, all right. Anyways, I don't even
Okay,
remember what I
so
was gonna
other
say.
constants in the universe.
No, wait, I wasn't done with
Oh,
light.
okay, continue.
So yeah, the like what we learned in class.
Mm-hmm.
Um, at first we treated light as a particle, right?
Mm-hmm. Yeah.
Or did we treat it as a wave
No, we
first?
started as a particle. I think.
Oh yeah, yeah. No, no, no. I think we did both in the same lecture.
Kinda.
Like because we looked at
Wave
the
particle
first we looked at
duality.
the double slit experiment, and then we're like,
Yeah.
oh, it's a wave. And then they looked at like the experiment where you do the double slit, but you take the brightness from like 0 all the way to, like normal brightness, and
I
then
mean, like the
what happens
intensity.
that
Yeah.
you record individual particles hitting the screen. And yeah, I mean, back in the day, like that must have been I mean, it still is super confusing, but like imagine just like witnessing that. You're like, oh, it's obviously a wave. And then and then boom, you're like, oh, well, if we treat it as a particle, we can actually like get a lot of results in like quantum mechanics and stuff like that.
Yeah, because it was originally that photons were always considered waves, and then Einstein proved it that it can also behave as a particle. And then at the same time, De Broglie, like Louis De Broglie,
Yeah,
um,
prove that it works
he
for anything.
he exactly. Then he proved the opposite with all electrons and protons. He proved that electrons can also be treated as waves because everyone thought they were particles.
Yeah.
So it was kind of the reverse, like. But it's
Yeah,
kind of like
something
Einstein
funny.
that started the whole trend,
Yeah, something
mainly.
funny is that like in class, um I think it was Julian. He was like, "Oh, like photons have um a wavelength, electrons have a wavelength, molecules and basketballs like
Hmm.
everything has a wavelength." But like I don't know, it's really hard to like visualize it. Like absolutely everything has a wavelength.
Yeah, it's kind of crazy to even think about, But like
Hmm.
wavelength, okay. It's not really that they have a wavelength. It's just
Yeah,
that like they can be
it's not an
represented
yeah.
as waves. They're
Yeah,
not
I'm not saying
really
like
like
yeah,
It's kind of hard to even think about because a lot of people think that these particles and stuff they are actually waves, but they just behave like waves. They have
yeah,
the mathematical properties of waves. They're not necessarily waves themselves.
yeah, I know what you mean. But going even further back in time, nice segue to our next topic is pi. Ooh, pi. It's not
Oh, the
obviously it's not I
very
mean it's
important constant.
yeah, not a physical constant, more of like geometry,
Yeah.
mathematical constant. And I'm pretty sure this is, I'm like 90% sure how they found pi was that they took a circle and then drew a square on the
Yeah.
inside and drew a
You
square
you
on
saw
the
the same
outside.
number file video I did.
Yeah, I mean, I
Exactly.
don't I don't remember it from number file, but
Yeah,
I
but like
just I just
that's where I
know like
remember it from. Yeah,
yeah,
he just
and
kept
then
drawing more and more
yeah, they kept drawing more and more vertices, and then the area
the
got
area approach pi.
nicer and nicer. It
Yeah.
approached the area of a circle, and then they took the limit, or I don't know if calculus was a thing back then, because
And
this was
divided
like
it by radius squared.
yeah, this was like what what was it like ancient Greece that they
Yeah,
discovered pi.
it was like BC, wasn't it? Yeah.
BC?
Yeah. Wait, I'm searching it up right
Oh,
now.
right, right,
Yeah,
right, right. Yeah,
first
yeah, yeah,
calculation
right.
of
Yeah,
pi was done
yeah,
by
BC.
Archimedes who was in BC, 287, 212 BC. That's
Hmm.
crazy to think about.
Yeah,
That
yeah.
that
I would
constant
love.
that was made over 2,000 years ago is still being
Yeah.
used.
Well, obviously, it's still being used.
No, no, no,
It's
no, no, no.
because
But I'm
like
just saying, like,
no,
it's
no.
so cool to think about that.
Yeah, it's being used because it's so important.
I know.
Like taken pi is actually everywhere. Like
Like,
even when
yeah,
you
I
think you're not
agree.
dealing with circles, boom, just pi out of nowhere.
You can really get, yeah, you can definitely get a pie out of anywhere.
Yeah,
Like, it comes in the
and
most unexpected places. I still
yeah, I would
remember some of
love
those limits and stuff we had to prove in class, or like some crazy
which one?
physics problem set
Oh,
question. And
yeah, yeah,
randomly, they're just like a pi squared or something that appears, and you're like, wait,
yeah,
what?
yeah,
This makes no sense, but it just comes up. It's just
yeah.
always
I would
there.
I would love to go back in the past where like nothing was discovered, like no calculus, and just like play around with geometry, you know? I feel like that would be so fun and like
Okay, but I
discover
don't
cool
think
things.
times would be very easy back then, you know? Like, you wouldn't
Yeah,
really
it's
have
not
time to
easy.
play with geometry.
Like, what do you mean?
Because I don't know, that'll
Some
probably be
people
like a
had
really
time.
strict ruler. You would probably be like a slave. You would probably be like working for him or
But
something.
I
I
mean,
don't know.
some people had time, obviously.
I guess so.
So
I
like
guess.
if I could go back and be one of those dudes who would just like a like every like notable figure was like mathematician, um physicist, philosopher, and like orator. Like
Hmm.
they were just everything at the same time.
They were mostly philosophers, actually. At that time,
I
it
mean,
was,
philosophers were also mathematicians.
yeah, because philosophers
Like,
were crazy.
yeah,
Like,
which makes
like
like a
back
lot of
then, like to be
sense.
a philosopher, was like like a really
Yeah, it was
high
like some,
level.
and like you could say something and everyone would be like, "Yo, damn,
This
like
guy's a
this
philosopher.
guy's
This guy's
onto
talking. Let's
something."
listen to
He'll be like, "Yo, 3.14. What? Oh,
him.
everyone's going crazy." But um, uh,
Yeah, I totally
yeah,
agree.
going back in time, yeah. Where actually, this is from last time. If you can go back to a point in time to witness the discovery of something mathematical or physical, what would you go back to?
That is a very tricky question. It seems like you already have an answer for this. You want to go first?
Um, I mean, I don't have like a definitive answer, but I think like like sitting behind Einstein while he's doing the general relativity equations would be crazy.
Sitting
Like
right
like
next
just
to Einstein.
just watching him go.
That would be for 10 years. You know that, right?
Okay, I
Because from
mean, yeah.
1905, when he published special relativity, to 1915.
Okay, I don't mean literally sitting beside him for 10 years. I just mean like going like witnessing his thought process and like I don't know, he's just a crazy dude.
I would actually love to just go to. You know what? I really thought I had that sentence, but then the more I thought about it, I realized it's wrong. I seriously do not know. Like there's so many times when I'm like, oh, that would be interesting.
Yeah.
Like
I
Galileo,
mean,
that would be really interesting.
yeah, Newton inventing calculus.
Newton just
That
sitting
would be
there when he's
insane.
like 21 years old inventing calculus,
Yeah.
like yo,
Yeah.
and we're just
Literally
and we're
he's
21
in
still trying to
quarantine.
understand calculus.
He's in
It's
quarantine just like, yo,
and
what if I just calculate
take
the
in
area under of this
he
curve?
made integrals before
Yeah.
derivatives.
Yeah.
That's nuts too.
I know that is nuts.
Like
Which is like, do you
it's
think we should learn integrals before
yo,
derivatives?
wait. Do you actually think he called derivatives anti-integrals? You know how we call them anti-derivatives?
Is that a thing?
No, I do not think so.
Okay, okay,
No,
okay.
definitely not.
Nah.
Sorry, what did you ask?
um, I don't even remember.
It,
Anyways,
it was right here. Oh, I forgot.
anyways,
This is
um,
terrible.
moving on past pi, there's e, which is Euler's number, which is
Came from
it comes
compound
up
interest.
yeah, it comes up from compound interest, and it's the highest, like to put it simply, it's the highest amount of money you can have after a certain amount of time
Hmm.
if like you calculate and add the interest an infinite amount of times.
Yeah, it's like 1 + 1/n whole thing to the n.
Yeah,
Yeah,
to
and if you
infinity.
take the limit as n goes to infinity, you get e.
Yeah. I don't
Yeah,
know if that
right.
was super clear. If you
Yeah,
if anyone's
I
listening
think
and they don't know what E is, I don't know if that was very clear, but it's the base of the natural, or the base of the log that makes the natural log. And
yeah. So e is also very
especially
important.
it's especially interesting to me because if you graph e to the x, the derivative, the rate of change of that function is that function.
That's
And the
crazy.
rate of change of that is also the function, and you could do that an infinite amount of times. And on top of that, the area under the curve is the function, and the area under that curve is, it just keeps going, which is
I
like
think
the
that's
coolest
really
thing ever.
interesting
Yeah,
that the
that's the
derivative of
coolest
e to
thing
the
ever.
x is e to the x. That's a
Isn't it
really
like the
interesting
only
fact.
function that does that?
Sorry?
It's the only function that has that property.
Yeah, that stays the exact same. That's pretty. That's pretty crazy. And also,
Yeah,
ln is also important because it's also like if you differentiate ln, you get 1 over x. And 1 over x is a very common graph. And it
yeah,
appears in very, very, very many things. So, like, even that's useful in many places.
right,
So
right.
like
And
ln and
also,
e, and that just comes up in all these places. You know?
yeah, and the thing about pi and e is that they're both irrational numbers,
Mm-hmm.
which is like why does that happen, like why is it that the ratio between the circumference and the radius is just never ending in precision, you know
That's
and
pretty crazy to think about.
same thing for like compound interest. Like, well, we relate it to compound interest, but it's not, it's good for more than just that. But why is
Oh,
like
it's
why
incredibly important.
yeah, but why are they irrational? Like, why couldn't pi be 2? Like, imagine if pi was an integer.
That would be crazy.
Like, what would the world look
I
like?
mean, I mean, if you think about it, engineers think of pi as an integer, as an integer.
Yeah,
They
I
think of
mean,
e as an integer as well.
yeah, but this is more like actual properties of circles that I'm trying to talk about. Like, imagine if the ratio of the circumference to the radius was like 2. Like, imagine if the radius was just half of the circumference.
That
Like,
would be crazy.
that would make zero sense.
I mean, it would make no sense in our world. Who knows
Yeah,
about another world? Maybe it's
yeah,
possible.
yeah.
I mean, who knows?
I
And
know.
actually, talking about e and pi, I think I think you've agreed with me on this, Parker. We've talked about this a lot. One of the most
Yeah.
beautiful equations in the world,
Oh
Euler's
yes, sir.
equation,
Yeah,
like the e to the I pi plus 1 equals 0.
yeah,
Like, I think that that's incredibly crazy because we're
yeah,
just talking
and
about constants, right? So, like,
yeah,
an irrational number raised to the power of an imaginary number multiplied by an irrational number plus 1 equals 0. Like, that's crazy to think about.
yeah. That is crazy to think about. But if you would have watched Three Blue One Brown's stream, um, his stream right now is about complex numbers, or like up to this point. I don't know if he's gonna change subjects, but he like decomposed the whole, like, starting from scratch with imaginary numbers, and then explained, um like, if you think about e to the x as the infinite sum that we learned in class.
Mm-hmm.
If you think of it like that, and then you take the properties about like vector addition or vector multiplication in the complex plane, it actually makes a lot more sense, because what happens is that if you have a real number in the complex plane and you multiply it by I, it rotates it 90 degrees, right? So if you have like 1, you multiply it by I, which is the unit vector that points upwards, you just get 1I. So it rotates that real number 90 degrees. And that's true for um like any vector in the complex plane. So if you draw a unit circle in the complex plane, you pick a point, and then there's an angle, right, related to that point on the unit circle. So if you multiply any vector in the complex plane by that vector in the unit circle, it will rotate your first vector by the angle of your unit vector on the circle. And so that relates to Euler's formula, um, because if you just look at the infinite sum, what happens is that you just rotate your, because I gotta formulate this differently because you start with 1, right? Because it's going to be x to the 0 over 1. So your first number is 1.
Okay.
And then what you do is you add um, a number. Actually, I don't quite remember how it goes
How
because
about we
like
just
some of
say
them
to
have,
watch the video?
yeah, just go watch the stream.
Just
It's
watch
a
the three
really
blue, one
it's a
brown
really
video.
good stream. But yeah, what happens is that you just add infinitely small vectors that are perpendicular to your first vector, and then if you rotate it pi degrees, then you just rotate once around and you're left with -1. So like, yeah.
Mm-hmm.
Anyways, that was a really bad explanation,
That
but
was a
trying
very
trying to
interesting explanation. I'll give you that.
trying to fit it into like
Yeah.
short form is
So we'll
not
just
that
say
easy.
go ahead and watch the three blue, one brown stream.
Yeah,
It's
three
really
blue, one
good.
brown, math lockdown. Just start from the beginning. It's a really great stream. Um, yeah, talking
What other
about
constants are there in the universe?
yeah, so talking about
Oh, a
vectors and
very.
stuff.
Oh, sorry. You continue.
Um, unit lengths, like unit vectors and stuff like that, that have a magnitude of 1 are in fact universal, right? If you go like if there's any alien civilization that discovers or creates, that's a debate, but
Mm-hmm.
they have math. One of the things that'll be universal is just the length 1. Like if you want to say I want to move 1 unit in this direction, it'll be completely universal,
Mm-hmm.
right?
That's true. And I think another really interesting constant is the cosmological constant from Einstein's field equations. Because
Right.
I really find it interesting because it kind of proves, well, not really proves, but kind of mathematically proves, in a sense, that dark energy or some type of energy exists where there's nothing in space, right?
Mm.
Because in the field equations, if you pretty much cancel out the curvature terms, that means like there's nothing there, like empty space. The field
Yeah.
equations still give you an answer of of how much energy is in that space. That means
Right.
even if there's nothing present, that means empty space, there's still energy in that empty space. Or at least this is what the field equations prove. So, and that is because of the cosmological constant. Now, even though the cosmological constant is known as Einstein's biggest mistake, it's
Mm-hmm.
still it's still pretty much um, completely invented the entire idea of dark energy. And
Does
and that's
that
kind of
come
what we're going
from
with.
does that come from the fact that he wrote his equations thinking or assuming that the universe was static and not
I think it was
accelerating?
something crazy like that. I actually do. Because I think Einstein was like not a believer that the universe is accelerating or something.
Yeah. Yeah.
And after he kind of showed it in the equations, he's like, "Oh crap, I made a
It
mistake."
doesn't work.
Yeah, exactly. And he's like, "I made the biggest mistake of my life." But in turn, that actually helped people who are trying to, go after dark matter and dark energy, especially. Sorry, not dark matter.
Yeah. I
So
don't know
yeah,
enough about like Einstein's equations to like have an opinion.
yeah.
But
So
yeah, go
they're
ahead.
just like, because I think the best way to explain them, because it can really be broken down into really easy terms. Like everything starting with an R has to do with the curvature of the space.
Yeah.
Everything with the G, like the metric tensor, followed by the cosmological constant, is pretty much that's that energy that I was talking about in empty space. And
Yeah.
everything on the right side of the equation represents the energy in that space. So left side represents like curvature, and the right side represents like energy. So like obviously this is not like a comprehensive rundown of the field equations,
Yeah.
but this is kind of like a basic understanding, I guess.
Okay. Awesome. Well, we're coming up on 30 minutes right now, actually.
Oh yeah.
Yeah. 29 minutes, 30 seconds.
Yeah, so I think
So,
today was pretty good. We had some nice talks
yeah,
about interesting constants.
I thought it was pretty interesting. We did have some other points to talk about, but, once again, we can also just talk about it in a future episode,
That's true.
which we're planning on doing pretty often.
Oh yeah.
Yeah, we do
Yeah.
have exciting interviews coming up soon,
Oh, I am
very soon.
extremely excited
I
and
think
a
we got
little
our
bit
first
nervous. I'm not
one.
gonna lie, a little bit nervous, but also excited.
Yeah, I still have to do research, think of some questions,
I'll have to do a
but
lot of research for sure.
that'll be awesome. Um, we got our first one, our first interview in 2 days.
Yep.
We're not going to spoil who it is, or I think we already did in the in the last one, but
No. I just gave them a hint of who it is.
oh, okay, okay,
I just said like
yeah.
what he does and the fact
I
that it's a
actually
he.
have, yeah. Go ahead.
Yeah. Okay.
Okay, so
Yeah. So, see,
we're just gonna cut it off
perfect.
there.
Perfect. Nice. Nice segue.
Okay,
Thank you so much for listening in.
well,
We're gonna sign off. I'm Ray.
yeah. I'm Parker. Thank you guys. We'll see you guys very soon. Got
See
some
ya.
very interesting episodes coming in. All right. See ya.
Stay hype. See ya.